My name's Andrew Burbanks, and I'm going to present some joint work with my collaborators Andrew Osbaldestin and our PhD student Judy Thirlby at the University of Portsmouth. So the focus of this work is on universal behavior in families of dynamical systems and how we can use computer-assisted proofs to establish parts of the explanation for these. So the simplest example are one-parameter families of unimodal maps with critical points of some fixed integer degree d at the origin. A prototypical example is that shown. And the case d equals 2, of course, is very well known indeed, and results in this very beautiful bifurcation diagram that's been the subject of considerable study over many years. The bit of the diagram I'm interested in to illustrate the technique is the period doubling cascade at the beginning. And certain features of this period doubling cascade are universal. That is, they're shared by very, very broad classes of maps. For the degree 2 case, well, one of the features that's universal is the ratio between successive spacings of period doubling bifurcations, and that ratio tends asymptotically towards a universal constant delta, around 4.669 for the case of degree d equals 2 at the critical point. And there is a similar universal scaling constant in the state space direction in the x direction, alpha. The key to understanding this sort of universality is to realize that a 2 cycle of a function f corresponds to 2 fixed points of f composed with itself. And so a small part of f composed with itself at the next period doubling bifurcation along resembles the original function at the previous one. So diagrammatically, if we zoom in on a region of the map around a fixed point, for example, and we adjust our parameter, increasing the nonlinearity to go through a period doubling bifurcation to a 2 cycle, composing the map with itself reduces that to a pair of fixed points. And the idea is that we rescale, and asymptotically, as we go further up the bifurcation tree, we find closer and closer resemblance with the original picture. So we can capture this idea of iteration or composition and rescaling by defining a renormalization operator R. So this operator R acts on functions G by composing them with themselves and then rescaling them, and we'll choose the rescaling typically to preserve some sort of normalization. In this case, I've chosen one that will preserve the normalization that the value of the function at 0 is 1. And Feigenbaum made a number of conjectures about this operator that help to explain the universality, the chief ones of which are that the operator has a non-trivial fixed point in a suitable space of functions, that this fixed point is hyperbolic, and that the spectrum of the linearization has essentially one expanding eigenvalue. It's easier perhaps to just draw a picture. In the space of functions, here's a quick sketch, and roughly speaking, the idea is that we have a fixed point G here. It's got a one-dimensional unstable manifold, and this universal constant delta turns out to be the corresponding expanding eigenvalue, and codimension 1 essentially stable manifold. So the goals in the sort of work that we do is to prove that such fixed points exist of renormalization operators, get rigorous bounds on them, and use these bounds to go off and deduce new results about broad classes of systems. Analytical proofs are possible. In fact, over the last 40 years, there's been an incredible amount of work done. Historically, though, these proofs have been extremely difficult to come by and have required some rather deep insights and developments in the subject. So a number of these questions were first settled by rigorous computer-assisted proofs, and that's the direction I'm going to show you today. So we have this renormalization operator R, and we would like to find a fixed point of it. In other words, we would like to solve this functional equation for the unknown function G star. If we think for a while, we realize that we can impose a symmetry. So we could write our function as some other function, capital G of capital X, which is x to the power d in this case. And we can write down the corresponding operator. So our operator R looks like, written in terms of this function, capital G we can write it as this operator t. So we can work with this symmetry reduced representation, and now it's a fixed point of t that we would like. And the first thing we have to think of is what sort of objects are we willing to entertain as solutions to our functional equation? In other words, what sort of space would we like to work in? If we think for a while about polynomials, the operation of composition with itself squares the degree of polynomials. So the only polynomial solutions are trivial ones. So we might look rather naturally then at functions which are analytic, so at power series. We immediately then, of course, have to think of what domains do these power series converge on. So that leads us to consider a space of functions which are analytic on some disk and satisfying a few technical assumptions on the closure of the disk. So think of these as a space of functions that can be written as convergent power series on this disk. If we equip this space of functions with the L1 norm, which turns out to be very convenient later, then it forms an infinite dimensional Banach space. And we can take as a Schauder basis just the monomials. So our first job then in finding a fixed point, and proving rigorously the fixed point exists, is to find an approximate fixed point. So to do this, it's enough to simply truncate our space at some finite degree polynomials, and I'm going to let P and H denote the projections onto the polynomial part and the high order part of the space respectively. So we can write any function in our space as the sum of a polynomial part and a high order part. Then the question is, how do we get an approximate fixed point? If I return to our little sketch in function space, these surfaces sigma n that I've indicated are the surfaces of functions having a period 2 to the n orbit of some given stability, and a typical one parameter family that has a period doubling cascade forms a curve in this space that passes through these surfaces. So we can find a point close to the stable manifold of our fixed point G by just following numerically period doubling bifurcations of our prototype family up to some very high number of bifurcations. That gives us a point somewhere here. And then we simply apply the renormalization operator repeatedly to move inwards along the stable manifold. So we do that as long as the quality of our guess seems to improve. And that gives us a crude guess. The question then is how we can improve it to get a good approximate fixed point. And the idea here is to adapt the ideas of Newton's method from finite dimensional calculus to our Banach space. So we write down the fixed point problem as a zero finding problem for an operator that's t minus identity. Then we can write down a one-step Newton operator in terms of our function g. And in here, dtg is the tangent map, the Frechet derivative of the renormalization operator at g. In other words, it's the linear part of this operator. The idea then is we iterate this Newton method in the space of polynomials of fixed degree to find a good approximate fixed point that I'm going to call G0. Here's what G0 looks like for the example of d equals 4. You can see it looks rather sort of quartic-like around the origin there. So this is a degree 40 approximation to the fixed point in the case of degree d equals 4 at the critical point. So the question now is, we have an approximate fixed point, but what I would really like to do is to prove that there's a real one nearby in the space. To do that, we want to do rigorous computations somehow in our function space, and we immediately hit two apparently insurmountable hurdles, which are that the function space is infinite dimensional, and secondly, that our computer arithmetic has limited precision. In fact, we can view these two problems as the same kind of problem and use a unifying idea to solve them. And the idea is this, that we abandon hope of dealing with single exact objects, and instead we settle for dealing with sets of objects whose bounds we can represent exactly in our computer. So for example, if I have a polynomial from the polynomial part of my space that I want to represent, I could bound it with a vector of intervals, and then it lies within the set of functions that can be written down as a polynomial with coefficients lying within our intervals. So I've abandoned dealing with the polynomial exactly and settled for dealing with this set specified by a set of intervals. What about more general functions in our space that have high order parts? Well, we can just add on an extra bound, this VH component, an extra upper bound on a high order function FH that bounds its norm. So in this way, we can bound any single function in our space now, we can bound. And finally, it's convenient to deal with balls of many functions in our space. So to do that, we simply add on another bound, VG, and you can think of this as the radius of a ball in the usual sense. So VG just bounds the norm of a general function in our space that we add on. And the resulting set of functions, we call it a function ball, and it's convex and closed. Convexity turns out to be very important for what we do later. The idea then is when working in a computer, we're going to choose computer representable numbers for all of these quantities forming our bound. And anytime we need to do an operation, we compute a new bound which specifies a function ball guaranteed to contain the result of the operation. And an easy analogy here is with interval arithmetic on the reals. If we have a real x and a real y, perhaps we can't represent them exactly in our computer, but we can represent them by intervals whose bounds we can store in the computer. And then provided that we are careful to ensure that we get a rigorous lower bound when we add lower bounds on our interval and a rigorous upper bound when we add the upper bounds, we can produce a new interval that's guaranteed to contain the result of all pairwise operations and therefore to contain the exact answer x plus y. In fact, this idea extends to our function space. We can, in this way, bound all the vector space operations, product, composition, and derivative followed by composition. You might want to have a think why we can't bound derivative itself, and also the norm. So we now have a framework for doing computations rigorously in a computer. How do we prove the existence of our fixed point? Well, let's return to the Newton operator. And the idea is to prove that the Newton operator is a contraction map on a ball around our approximate fixed point. We know that the renormalization operator isn't a contraction because it has this expanding direction, but close enough to the fixed point, we would hope that Newton's method is. And there are 3 ingredients in doing this. We bound how far the approximate fixed point moves under Newton method. We gain a uniform contractivity constant, so this bounding all pairwise contractivities. And finally, we have to ensure that our ball is mapped into itself. Again, it's easier to see this with a picture. I've got my approximate fixed point G0. I form this ball around it of radius rho. I bound how far the center of the ball moves, and I come up with a bound on the image inside a ball of radius kappa times my original radius. And then if the inequality at the bottom of the screen is satisfied, then indeed the smaller ball really does lie within the larger one. And we can apply the contraction mapping theorem. How do we get these bounds? Well, the first bound is easy. We can put a trivial function ball with high order and general radius 0 around our approximate fixed point and use function ball operations to get this bound epsilon on how far it moves. Then we can choose a rho larger than epsilon to form our larger function ball of radius rho. And then we're stuck because we've got to get this uniform contractivity constant, which looks quite hard to do. But we can borrow ideas from finite dimensional calculus and use the mean value theorem. Because function balls are convex, the line segments joining any pair of points in a function ball are also in there, and one can do a one-dimensional argument along line segments. So what we do is bound the norm of the derivative. In fact, we bound the norm of the action of the derivative on every basis element in our space, and that turns out to be enough to gain a contractivity constant kappa. How can we do this? Well, for the polynomial basis elements, it's quite clear how we can do this. We just put trivial balls around them of radius 0. But then infinitely many basis elements remain, of course, because it's an infinite dimensional space. But thankfully, we can come up with a single function ball with high order radius 1 that contains all of these high order basis elements. So we can capture them all with a single computation. So one can do this for the d equals 4 problem. Truncation degree 40 in our symmetric representation is enough. And we gain bounds on the corresponding universal constant alpha and on the fixed point function. The second application that we can use this technique for is in bounding eigenfunctions and their eigenvalues, in particular this expanding eigenvalue delta. To do this, we just simply adapt the idea from the fixed point proof, and we rewrite our eigenproblem as a root finding problem. And then the idea is to remove the eigenvalue from consideration by embedding it as one of the power series coefficients in the eigenfunction. Remember, eigenfunctions are only defined up to some normalization anyway, so we can take advantage of that spare degree of freedom and extract the eigenvalue by some linear coordinate functional. So then we aim to solve what's now a nonlinear eigenproblem in V, and we can do that again by proving that the corresponding Newton operator is a contraction map around a suitable approximate fixed point of the Newton operator. And doing this gains us, so this is just a sketch of what the eigenfunction happens to look like for the case, for the delta eigenfunction for degree 4, and we gain bounds on the corresponding eigenvalue. Finally, one further use, which I think is rather a nice one, is that we can ask the question of what happens if we take the iteration of a one parameter family and add on a small amount of noise. So in the simplest case, we just pick some IID random variables independent of X and add them on. And then it turns out that in the case at least of deterministic definition of scaling in our renormalization operator, we get another eigenproblem. In this case, this linear operator L is related again to the Frechet derivative of our original renormalization operator. And what's rather beautiful in this case is that one of the eigenfunctions controls how the shape of the distribution changes when we renormalize, and the corresponding eigenvalue controls by how much the total variance gets scaled when you renormalize. And one can again use a similar contraction mapping Newton argument to bound this corresponding eigenfunction as illustrated here, and the corresponding eigenvalue responsible for the universal scaling of the noise. So initially our concerns were simply to get bounds on these objects, but in fact with a bit more work and by moving to a high performance language, in this case we used Julia, which is fairly new high performance language, one is able to improve these bounds significantly. So by going to much higher truncation degree and using multi-precision, we were able to go up to degree 640 in our symmetric representation. So that's degree around 2,500 for the original function. And we were able to bound the fixed point within a function ball of radius 10 to the minus 331, for example. And because this is an L1 bound, it's the sum of all of the absolute errors, then every single power series coefficient is at least that accurate. So this was a very satisfying thing to do. And we gained similar bounds on the delta eigenfunction and the noise eigenfunction. A side effect of this, of course, is that we're able to prove, probably for the first time, I think, that certain digits of these universal constants are definitely correct. There are many numerical computations of these. This method gives us rigorous digits, for example, 325 in this case for delta. And one final application, we can use the function balls that we've obtained to extend the domain of analyticity of our functions, to get analytic extensions to domains that are much larger than our initial disk. Essentially, we use the fixed point equations recursively along with the function ball obtained. And finally, by coloring or identifying places where our function maps its argument into the upper or lower half plane, one gains a tiling of the domain of analyticity by the so-called Yokos puzzle pieces. This has been well studied in the case for d equals 2. This is an illustration in the case d equals 4. Some further work that we've done, we've been able to bound the spectrum directly for our original operator and the symmetric reduced one in order to prove hyperbolicity. We've looked at other even integer degrees and indeed odd degrees by modifying our fixed functional equation. and we're able to get bounds on the dimension of the attractor at the accumulation of period doubling. And this work forms a sort of starting ingredient for work we want to do on coupled systems. So I'll end by thanking my collaborators again, and thank you very much for your attention.